I guess technically it's only been a minute, but I started looking at this one. The base function is 1/4 to the x. We have a vertical stretch of 2. Technically, the negative is a reflection. It's not a negative stretch because that doesn't make any sense. We have a horizontal translation of -5 and a vertical translation of +3. That's something that came up in the assignments that I've gone through for transformations. If the very first question, there was a table. And there's some people for this one that would say -2, and then the reflection, they would say it's in the x. And it's like, well, technically, if you're saying there's a reflection, that doesn't need to be there. So, but that's there. I know have been some teachers that have said it should be there, and I've argued, and everybody has there. That's not what I wanted to hit at all. Just want to make sure. Okay, we're good. Key points, x and y, -1, 1/4. Oh no, because this is y equals 1/4 to the x, -1 and 4, 0 and 1, 1, and 1/4. So when we transform this, -1 minus 5 is -6, -5, and -4. That's all right. -2 times 4 is -8. -8 plus 3 is 5. -2 times 1 is -2 plus 3 is 1. -2 times 1/4 is -1/2 plus 6/2. So that's 5/2. Which is 2.5. So 1/4 to the x would be some sort of exponential decay because we're reflecting it in in the x. We're starting down and we're going this way. So let's see if I can pull this up enough that we can. This one we have a horizontal asymptote is y equals 3. Oh, we're gonna have this issue today. Awesome. Yeah. All right. Smart Notebook is so wonderful that it randomly hasn't. So there's our horizontal asymptote. -3, 1, 2, 3, 4, 5, 6. -3, -5. -5 and 1. Oh, okay, yeah. -4 and 2.5. So this one kind of would. Oh gosh, that's awful. Our horizontal asymptote. Kind of like. Yep. Go for it.
Are you going to be doing one of these videos on Monday morning?
On next Monday morning?
Yeah, because it's like a holiday.
Oh, that's a good question. If it's a holiday, technically, no. I thank you for reminding me. I hadn't even thought of that. I will.
I was just wondering because I'll be at the trailer with my Wi-Fi, so I didn't
Oh,
know.
oh no, no worries. Monday's a holiday. It wouldn't be. Uh, cancel Monday's stuff. Thank you for reminding me. I keep hearing about this long weekend in May, and I was like, I don't know. It's been one super giant long weekend because I mean I haven't really done much. Domain. This is reals. Range y is less than 3 because this one's flipped upside down, and that would be that. I don't even know what day today is. It's Tuesday. I know that because importantly, the drive-through at Java Moose is opening tomorrow, so I can go get. Not that I can't make coffee here, but it's just different. The next assignment technically is due there, so I don't. I might hold off a little, or put one up, but it will be this in the beginning of logarithms. So if I put one up, half of it will look different, even though we're going to start logs on Thursday. Oh, wow, this is all confusing. So there is our graphs. Again, like I said yesterday, and once we kind of have this transformations business done, if we know what the base graph looks like and the key points look like, we can write a mapping rule. We can change our table to give us these sorts of things. I mean, eventually, some people are able to just say, okay, well, my asymptote's at +3. It's reflected in the x, so it's going down. So it's going to be like you can just say, asymptote's there. It's moved, so the graph's going to look something like that. You have an idea where it is, and that's the whole thing about getting comfortable with this sort of thing. Um, so that's graphing in a nutshell. Transformations to model a situation. So this is, there's two examples about writing an equation, and where I stole this, used C as the base because B is our vertical stretch, horizontal stretch. A cup of water is heated to 100 degrees Celsius, then allowed to cool to a room temperature of 20 degrees. The temperature T is plotted on a coordinate grid as a function of time. So this is temperature, this is X is minutes. It is found that the temperature decreases exponentially at a rate of 25% of the previous temperature every 5 minutes. So what we're going to do is build a thingamadoohicker equation based on that to model this situation. So we have to figure out a couple things. This is going to be key. Um, that's going to be kind of important. And we have some numbers here. So 25%. So what the temperature drops by 25%. When we're looking at a curve like this, we're actually looking for what percent or what portion of the temperature remains. So if 25% goes away every 5 minutes, what is left every 5 minutes? Well, it's the rest of the whole. So we keep 75%. So we can use this, the base function is going to deal with that. Now we can use it as our kind of base equation. What is going on? Why is that not working today? Let's try this again. Okay, I turn the airliner off and then it doesn't want to reconnect again. And if that doesn't happen, oh, here we go. All right, so can I move that? So the exponential function is y equals 3/4 to the x. You can also do it kind of as 0.75 to the x. Um, or, sorry, temperature is. So we have these 5-minute intervals. After 5 minutes, it's like that's 20, so that's 10. 5 minutes should be somewhere in there. It's about 75 degrees. But then, like, the first one is easy. But where we, so if the time is in intervals of 5 minutes, so t is a rational exponent. If it was every minute, we would just use x. Well, I'm going to use x for time just to make things simple instead of capital T and little t. So if it's every 5 minutes, our exponent is going to be this, because instead of having it 1 minute, we're looking at every 5 that it goes down. So when we have something that is every so many minutes or every so often, it ends up being a rational exponent because we're stretching our time out. So now we have temperature equals 3/4 to the x over 5. So that's our first step. Horizontal asymptote is nice and simple. We know what the minimum temperature. Hits room temperature if you have a cup of coffee on a table or tea or whatever your warm beverage of choice is. It's going to start out hot. And eventually, because of the laws of thermodynamics, if the room is 20 degrees, the water is going to end up at 20 degrees. That's the way it goes. So the horizontal asymptote for this situation is 20 degrees, which is the air temperature of the room. So now we have T equals 3/4 x over 5 plus 20 because that asymptote has moved up 20. Well, this is represented, that means the function has been, well, sorry, this whole thing needs to go there. Somehow, I forgot the equal sign got lost. So now we have effectively the asymptote. We know our kind of time. The t-intercept is way up here. It's the point 0 and 100. So that gives us some information. Because technically we have an a value here, which we haven't figured out. We can use, because that's not 0 and 1, there must be there's a vertical stretch. Because that 20 is there, we can't just say, oh, a is 100 and go from there. We have this point. Well, there's our x. There's our t. If we have everything here, we have everything here, we can solve for a. So 100 equals a times 3/4. Oh, 0 over 5 plus 20. Algebraically, I'm going to move that over there. 80 equals a. 0 divided by 5 is 0. Anything to the power of 0 is 0. So our A value is 80. So we have our A value. It's not shifted left or right because that doesn't make sense. We have an intercept. So now we have temperature equals 80 times 3/4 to the 0 over 5 plus 20. Gosh, not 0, but x. Put our variables back in. So we have our equation. We can kind of check this to make sure. We know after 5 minutes, it should be, let's see. For some reason, I think I may have. For 5 minutes, that's 1/3 of 80. What have I, because what is the temperature after an hour? Well, oh my lord. After an hour is going to be right there. But that, oh, maybe it's, stop that. Let's just take a look. 10 minutes, or well, 20 minutes, I can see is going to be, what, 43. Let's see if that's going to work out, give or take. Well, 80, 10 over 5 is 2. 3/4 squared plus 20. Here's hoping. 0.75 squared times 80 point. Now, what did I get there? 60. Oh yeah, 10 minutes is 65. Why did I was looking at that. So yeah, we're okay. Temperature after an hour. This means x equals 60 degrees. Temperature equals 80. Have confidence in yourself. 60 over 5 plus 20. 60 divided by 5 is 112. So 0.75 to the power of, well, just to make sure, 60 divided by 5. Close the bracket. Gives us that. Times 80 is about 22.5 degrees. Which, looking at our graph after an hour, we're slightly above that, so we should be pretty good. So that is an exponential decay. That's kind of a common one. We can do half-life, and because this one has a horizontal asymptote, that's why I'm second guessing myself. But because it's a horizontal asymptote, that makes sense. But we're just looking for an equation. So that's a decay. And then there's this question, which is a variation of one that I used to use all the time when I did exponential functions, but I used to say Mr. Bellier was making some sort of virus to be mean and evil. But now he wants to make a super genius virus that he infects initially 10 people. The population is infected. The number of people doubles every 10 days. How many things are going to be left? Or how many people will be infected? So I have double every 8 days, 10 people. So this one is actually an exponential growth. We can't go really back in past there. Um, but we have initially 0 and 10. After 8 days, we would have 8 days, we would have 20. How many are we could you could keep doing this sort of thing, but that doubles tells us our base function is y equals 2 to the power of x. Every 8 days instead of every day. Um, this is, so there's our base. This is our horizontal stretch. So we would have y equals 2 to the x over 8 because it's doubling every 8 days. So this one is a little bit easier. So we have to find our a value. The asymptote hasn't shifted because it's not going down. Technically, if we went into negative time, it could go there. This one, our 0 and 10 tells us, well, 10 equals a times 2 to the 0 over 8. So 0 over 8 is 0. 2 to the 0 is 10. Well, that's 1. So a equals 10. So our function is y equals the initial 10 people times 2 to the power of x over 8. There's no adding or subtracting, and this is for just straight exponential growth. You can model a lot of it. X over, let's put a c in there. Initial population. If it's 10, 5, 4, 2, and this is the b value is how frequently we, in this case, double or change how often the base happens. If it's a financial one, well, if you're earning interest, 1.03, you're earning that every 2 months, every 6 months, or anything like that. So these are in, I think, GMF. We talk about it a little bit in financial and workplace about what the curve looks like for compound interest. How many people would be infected after 10 days or 50 days? Well, days is X. Oh dear. 10 times. Pull out my handy dandy calculator. 2 to the power of, this is where brackets helps because 50 divided by 8 isn't a nice even number, but it's 2 to that power to the 6 and a quarter. 76.1. So after 50 days, we would have, that's 767. Now, where this sort of stuff goes, how many people are going to be infected after 50 days? The other question where this leads to In fact, because we're making super geniuses, we're not really infecting people. How long would it take to infect 1,000 or 10,000 people? Well, if Y is the people infected, 1,000 equals 10 times 2 to the x over 8. Well, getting the 10 away is easy. So 100 equals, does anybody know how to get that x on its own? And this is the problem with exponential functions and where we need to go next. To solve this problem, you need to be able to do the inverse. If this was x squared, well, that's easy. We take the square root. And it's not something that we've come across before. And you can do this by like trial and error. Okay, well, 761 was 50. I could say 2 to the power of 60, but we're looking for 100 in this case because of how the math worked. Well, that didn't make a whole lot of sense. No, yeah, 55. Well, that's 117. To get it, you can trial and error this, and you can go back and iteratively. Well, we went from 60 to 55. Whoa, to 53. So it's going to be between 53 and 54, and you can keep going. But there is an actual mathematical method to do things, to do the inverse of an exponential function. Logarithms, and that's what we'll pick up on Wednesday. A logarithm is the inverse of an exponential function. And it's, you see the button on your calculator. It's not actually, oh, there we go, log. And there's another one, it's called ln, the natural logarithm. Um, and we will go to there on um, Thursday and start talking about those. We just start talking about them initially as how to translate them from one to the other. Um, but some people think they're ridiculously intimidating. They're actually not. We'll show you all sorts of tricks, but they involve solving for that one. 53.1508 blah 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 days. So 53 is pretty close, but that's where we'll stop now. The second assignment, or the assignment on radicals, and I can't remember what the other inverses, I think, is due later this week. Get as much done as you can. And yeah, that's all I have to talk about today. If anyone has any questions, I'll
Mr. McKay, I have a question.
go for it.
I don't know if you covered this or not already, but my computer was being really slow and it wouldn't let me on until like halfway through this.
Okay.
But for like the homework thing that you gave us yesterday, or like that little question,
This one?
How did you get your first graph for your key points table? Do you know what I mean?
So it's 1/4 to the x, right? Like that's our base function.
Oh, okay.
So -1, 0, 1, and that one's always going to be this, like it's always going to be 0, 1, 1 and whatever the base is. And then you're going to
Oh, okay.
do the inverse for those ones. Like if this was 4 to the x, it would be 1/4 and 4, or 1/2 and 2. Like those ones are always, like the -1 and +1 are always going to be kind of inversely related.
Okay.
Okay?
Okay. And oh wait, I have another one. How did you? Wait, could you scroll down to your graph for a second?
Yeah.
Okay. How did you know? Like, is it? No, actually, never mind. I figured it out. Okay.
Yeah.
I'm good.
Okay. Perfect.
Thank you.
You're welcome. Anybody else? If not, I would say enjoy the sun, but it's kind of drizzly here. Hopefully the rain's gonna stop soon. If not, have a good day and see you guys on Thursday.